Hello, everyone. In this video, I'm going to talk about the superposition principle and n-determined coefficients revisited. And this is kind of the next theorem after working on n-determined coefficients, which kind of a simple observation, after working on examples of undetermined coefficients and looking at their structure. And it helps us to extend the application of these method of undetermined coefficients and enable us to solve initial value problems, which means the IVP for non-homogeneous differential equations. Because if you look back at undetermined coefficients, method and examples, we were kind of satisfied with staying with that particular solution. And we need to generalize that because we want to solve IVPs, right? So that's kind of the purpose here. The superposition principle is, it is here. It's kind of straightforward. It is a theorem. It just says if you have this linear second order differential equation and it's non-homogeneous, and you have f1 of t as non-homogeneity there, and you have let's say if I have this and if y1 is a solution to this, and if y2 or y sub 2 of t is a solution to the same differential equation, but with a different non-homogeneity, which is f of sub 2, and all kind of dependent on t. Then if you run into this, then any constants, any constants, k sub 1 and k sub 2, the function k sub 1 times y sub 1 plus k sub 2 times y sub 2, or k1 y1 plus k2 y2 is a solution, is also a solution, but to this differential equation, same thing on the left-hand side, but the right-hand side is that combination. You see, kind of straightforward. If you know the solution to this differential equation with non-homogeneity first one, then you know for the second one, then a combination of these solutions will work for this non-homogeneity here that you have. Can we prove if this is correct? Yeah, actually the proof is just straightforward, because what will happen is if you plug in k1 y1 plus k2 y2, which we say the solution, right? In the differential equation. And you can factor K1, and K1 goes for these terms, right? You will see that you built back a differential equation with y sub 1, or the first solution. Then for the terms of case, that's the, and this is like the given, right? And the next one is the given. So the proof is kind of straightforward. Superposition is really cool. I've used it in some research in the past, in actually engineering, to build some problems based on the solutions. So it's interesting. It allows to expand these indeterminate coefficients method. I think we can do some examples, but let's give you, because of that, something important to know, that if we have, if yp or y sub p of t is a particular solution to this non-homogeneous equation, and we can add to it, we can add to it a general solution, which we did C1 Y1 plus C2 Y2 C sub 1 times Y sub 1 plus C sub 2 times Y sub 2. Of course, when we did this of the homogeneous equation that is associated with, let's call this equation star. So if you have this equation star, or this linear equation here, put it as second order, and it's non-homogeneous, then if you look into its homogeneous form and you find its general solution, and you can add that general solution to the particular solution, then the sum, which based on superposition principle here, all right, let's write the sum first. Then the sum here is gonna give us the general solution. The sum is the general solution to the equation, which is y sub p of t, which is a particular solution, plus the general solution to the homogeneous case. We can do the same thing again. We can check it and all that. So this is kind of important to know. Now that's the goal. That's why we did this superposition principle. And now we can move beyond the particular solution to the general solution. then we can solve the IVPs. Of course, you can see here, there is a theorem that we can do, but you can see here that the parameters here, of course, are 2, right? And as we discussed in the past, that means we need kind choose 2 equations, which we did 2 initial conditions to solve for these and come up with them. So we can, there is actually another theorem that deals with this, which is the existence and uniqueness for non-homogeneous case. We did the existence and uniqueness for the homogeneous case. But since we already understand this, we're not going to too much emphasize on existence and uniqueness and prove it. Um, it's kind of course, as I mentioned, it's important for us to know that the solution exists and it's unique and all that. Well, we did it in the past. So here, instead of kind of going back to that, it's just important for us to know, since we're running two parameters here, we're going to need 2 conditions. And this theorem that says that if you have the A and the B and C, of course, coefficients, constants, that's important here. We're still dealing with that. So they're not variables, they're still constants. And also if you have, in the initial conditions, let's say I have y of t naught small 1 here is, let's say capital Y not here. And the other condition, initial condition, y prime of this small t naught here equal y1. So if I have this, and of course I have it's connected, this equation star here, then this theorem kind of, I'll summarize it for you. It says, of course, if you have the ABC, A is not 0, they are real numbers. And of course, we have these T naught and Y naught and Y1, all are real numbers. And of course, you have a particular solution to this problem and some interval that contains, of course, T naught. You want the interval to contain T naught like we did in the past um, of the initial condition. And of course, y1 and y2, we talked about that they need to be linearly independent to the associated homogeneous equation, right? We know what that means. Then there exists a unique solution in I, in that interval, to the initial value problem. Okay. So so to summarize for you again, this theorem, it just means that if you have these interval and the initial condition is that in that interval, and of course we're talking here about the case where we have real numbers for the ABC and everything else, not variables, and of course y1 and the solutions are independent solutions like we did in the past. Then there exists a unique solution for the IVP. And there is a proof to it, of course, but focus a lot, when we focus a lot more on this, we start to lose the sense of what the superposition principle is doing and how the general solution is formed. So let's return to that and let's do an example. first, and kind of talk about this IVP thing. So let's say you're given that the particular solution is this. To this equation. Find general solution and a solution satisfying this IVP. So find general solution and solution satisfying these initial conditions. So as you see here, we're not given to check whether this can be done or not. We're given that, when you look at the particular solution, you look at the initial conditions, there is no issue there. So we know that it's going to exist and it's going to be unique. So let's focus on this principle. So the corresponding homogeneous equation, of course, is this, right? Which means the auxiliary or characteristic equation is going to be this, which means the roots are expected to come up as plus or minus 1. And they are distinct real roots, which means the general solution comes up in this form of the homogeneous case, right? So send YP is given, YP here in this case, sorry, I think here I rewrote that twice. YP is just T squared, so YP is given. Then now we can say that for the non-homogeneous equation, then the general solution is y of t equal the particular solution plus the general solution for the homogeneous case. So it's not bad. It's just understanding. Maybe write it here as, we can write it this way. And even remove this t. We know it's all function of t here. So we can just say this way. So this is what we're looking for when the question is find a general solution. And now that you know the drill, you know what we need to do. We're gonna go into initial conditions, and you're going to use the first one. And you're going to find the first derivative to this. So t squared becomes 2t. So right. Then you keep going. These just the chain rule will give us a negative. All right, so these will lead to C1 equal C2 equal 1/2. And from there, we go back to the general solution, and we say it's t squared plus 1/2 times this function. All right, it's done, but in the same time, you can also recognize that this is the hyperbolic cosine in calculus. So if you want, you can do the extra step. All right, so I think we can do more examples, and the takeaway of all the examples we're gonna do is an, a kind of, let's write it here. Maybe I'll do a new page, then and I'll do another video with more examples. So method of and determine coefficients, kind of revisited. We have defined particular solution to this differential equation. And let's say we do a case where you have a polynomial with some degree m, and we have RT. This is a polynomial and degree m. Then we can use the form for the particular solution, t power s, and times a polynomial built with these coefficients, but the degree is m. And this is what we did in undetermined coefficients. So S is 0 when R is not a root. For the auxiliary equation, S equal 1 when R is simple root, and S equal 2 when R is double root. Of the associated. All right, so that's when you have the polynomial times the exponential function with RT. So what if it's the other case where you're running to cosine and sine, or uh, on the right-hand side in the non-homogeneity side? So here we're going to take advantage and add more. So to find something particular solution, this the left-hand side is same. But the right-hand side, if you have a polynomial times exponential function times cosine beta t plus some polynomial degree n, the same exponential function and sine beta t. Of course, here this is polynomial degree m, polynomial degree n. What else? Then you can use uh, same thing for the particular solution, uh, just like we did before, t power s, some polynomial k degree here. You see here, you have 2 alpha t is the same, sine beta t. So here, the important part is what is S now? What is K first? Let's do K first. So K, you see, we're using the same. We may have different degrees, but in this particular solution, we're using the same degree to K. So K here is the larger of M and N, is the larger degree of M and N, right? That's the important part. Then we can go back to say S is 0 if alpha um, plus I beta is not a root. S equal 1 for alpha plus I beta is a root here of the associated. That's the equation. All right, so maybe give you kind of a quick sketch, then I'll do examples where we're actually solving them now. So let's just do a quick example here. Let's say you have this equation. The goal from this one is not to solve in detail, but just to talk about what we just did. And then in the other video, I'll do examples where we solve in detail. All right, so the roots associated with um, r squared plus 2r plus 2 equals 0 are -1 plus minus I. And if we compare these, we can see that the particular solution, let's look into, do we have t here? We have t here, we don't have t, so let's put t power 0. So k is 3. All right. Okay, what is alpha? Alpha is here. Alpha is -1. What is beta? Beta is there. Beta is 1. Let's compare it to this, which is alpha plus minus I beta, right? So yes, so here, based on this conclusion, S equal 1. Okay, so now let's write the particular solution. So t power s which is 1. We need some polynomial with kth degree, which is 3. Times the exponential function times cosine t. And we just repeat. We change the coefficients to b. And times the exponential function and times sine of t. All right, so the method of undetermined coefficients apply also to higher order linear differential equations with constant coefficients. And maybe if we do chapter 6, we'll, based on this book here that is shown, this textbook, then we will talk about that. And that will be clear. But just you need to know, of course, that the method can also be used to a higher order, but we're using here a second order and linear equations, constant coefficients. Okay, thank you.